For lecture 15, we'll look at solutions to ordinary differential equations and how this is different from our previous lectures is we are considering boundary value problems instead of initial value problems. Um, for this topic, we'll cover only two methods, and they are the shooting method and the relaxation method. So before I go into that, just a recap on what we have done so far. So in the previous few lectures, we have looked at solutions to this kind of ODE, where we are given the value of y at t equals to 0, and this is some given value which we will call y0. So in the axis of t, you are given the value at t equals to 0, which is the first point, and you're asked to solve this ODE for all the time scale that is involved in your t. Okay, so this type of problems where the initial value is given is known as initial value problems. And the techniques that we have learned to solve these initial value problems are basically Euler method, Hoynes method, the midpoint method, as well as the Runge-Kutta method. So these kind of initial value problems appear in a lot of your engineering problems. For instance, in chemical reaction, we can define a chemical reaction by this ODE here, where your C is your concentration of your chemicals, and you're always given given the condition at t equals to 0, or just before the reaction starts, you usually know what your concentration is. Okay, another example would be tissue damage due to temperature increase. So the equation governing the tissue damage is given by d omega dt, and this is expressed as the following exponential function here. Okay, so again, before the heating, we always know what is the condition of your tissue damage. So in most cases, there will be no damage at all. So the amount of damage in your tissue during your initial condition is usually 0. Okay, so this kind of ODE are known as this kind of ODEs where the initial values are given. They are the initial value problems, and we have learned about the few techniques that we can use to solve them. So what we want to do in this lecture is to solve this type of ODE. Again, you have a first order ODE, but right now, instead of knowing the value at the initial condition, you are given the value at the end condition or the boundary condition. Okay, so in the axis of x, the first point, the value of y is unknown, whereas at the last point, this is given by some yn value. So this type of problems are known as boundary value problems, and this is what we're going to consider in this lecture. So to start off, I'll just use an example. So let's say we have the ODE dy dx, and this is given by minus 3xy. So you're given the domain where your x applies. So this is from 0 up to a value, let's say I'll call it xn, just to use some values. For example, this is from 0 to 1. Okay, the value at y0 is not known, but you know the value of y1 is basically given by some value. So let's say I'll call this 10. Okay, just for example. Okay, one way to solve this is, since we know the techniques to solve the initial value problems, what if we simply make a guess on our initial value? So what if I assume, or I guess, my y0. So let's say I call my guess a y of superscript 0 as my initial guess. So my y0 is, let's say if I assume y0 to be 1. Okay, so if I assume my y0 equals to 1, and for the moment, if we ignore this boundary condition here, this problem would become an initial value problem because we have made a guess to our initial value. So we can solve this ODE now using the Euler method, the Hoynes method, or the other methods that we have considered so far. But for this particular example, we can actually solve this analytically. So we can write 1 over y dy minus 3x dx. So what I've done is I've just rearranged this equation to write it as an integral. Okay, so your integral from y would be from your y0 from your guess up to yn. Okay, and your integral for x will be from 0 to 1. So basically you can integrate this, you'll get log y from yn to y0 0, and this would be equals to minus 3 over 2 x squared 0 1. Okay, so just substitute in these values and you'll get log yn minus log 1. Okay, because we have assumed our first initial value to be 1. Okay, so this would be equals to minus 3 over 2. So you can rearrange this to obtain your yn. So yn is basically log 1 plus your yn is basically your exponential log 1 minus 3 over 2. Okay, so this would be given by a value. So what you want to do when you have obtained this value is to check. Okay, let's say for consistency, this is the value that you solve. So the superscript 0 here corresponds to the guess or your assumption for your initial condition. Okay, so you want to see what this value is. So what you want to do is you want to check if your yn guess is the same as your yn. So in this case, your yn is your y1, which is the value of y at the last point. Okay, so if this value is equals to 10, what this means is that your y0 0 of 1 is your exact initial guess, because when you solve it, your boundary value is the same as your boundary value that is given by the problem. But if it's not the same, it means that your guess is not correct. So what you can do is you can do another guess. Okay, you can do another guess, and let's say now I'm assuming it is to be 2. So using the same method as shown to you here, you can find out what is your yn again. So carrying out your integral, you can find out what is yn1. Okay, and you'll have some particular value here. Okay, so again you check whether this condition is true. Okay, so you check whether yn1 is equals to y1. If it is not the same, then you have to move on to your y for your second guess, and you just make any guess. Of course, it has to be an educated guess, and you keep on doing this until you reach the condition where yn k is equals to y1. Okay, so this method is basically known as trial and error, because you make a trial, you solve a solution, and you determine the error. Okay, so let's say I've made a lot of guesses. Okay, so let's say I've made guesses from y0 0 up to y0 100, which means I'll be able to get the same number of boundary values as well. Okay, from all these 100 guesses, I'll be able to estimate the boundary value, or 100 boundary values. So this means I can plot out the values of these two in a graph, where this is my yn(k) and this is my y0(k). Okay, so if I plot that out, where this axis is all my guesses for my initial value, and this is all my yn values obtained from this initial guess, I'll be able to obtain some plots here. So let's say my plot looks something like this. Okay, and my exact value for yn is actually 10. Okay, this is given by the problem. Okay, this 10 here is given by the problem. So let's say my 10 is here. So if I extend this out, this line, this dash line is what we call my yn is equals to 10, which means the intersection or the point or the cross section between this line and this red curve here, if I extend this down to the y0 axis, this would be my initial value. Okay, so I'm going to repeat. If I from all my 100 guesses, I'll be able to obtain 100 boundary values. So in other words, if I can present them in a data form, okay, I'll have my y0k and my corresponding y and k. So if my first initial guess is 1 and this is 0.1, for example, then I make an initial guess of 2 and I get 0.6. So I have all my values up to the 100 point. Okay, so I can plot this out as a graph, and for example, if I get this red curve here, this would be the plot corresponding to all the guesses and the boundary values that we have obtained. And since this is known from our problem, then if we extend this constant yn line out, the point where this dashed line intersects with our red curve, if we extend it down to the y0 axis, this would be our exact initial value. Okay, so you can do this by plotting the graph and then trying to find out what this value is, but again, this would not be very accurate. Okay, and it is also not systematic, because what we are doing is we are randomly placing our initial guess to find what our yn values are. Okay, so we need a more systematic approach, and this is what we'll talk about in the next part.